I always use sunglasses when I'm outside. I particularly like these right here. These are a landscaper's type of safety glasses. I like them because they're impact resistant, UV blocking, and they work real well for what I do around here on this farm. Now, these are not polarized. These sunglasses here, a different brand I have that are polarized, but they're not impact resistant, these particular ones, so I usually don't wear them a lot working on stuff. But what's that really mean? Polarized versus non-polarized. Let's take a look at that, and what we're going to do is start out, first of all, understand what that word means. Polarized. What are they talking about? We'll take a look at that now. Most of us don't have the need to wear sunglasses inside. After all, they call them sunglasses. That's to block the sun when you're outside. So let's take a little closer look. What is sunlight and what does polarization really mean? We're going to dig into it just a little bit here. This is a real good article from Wikipedia on the electromagnetic spectrum. I'd highly encourage you to go to this. I'll put a link in the description. If you go down here to this chart here, see if we can blow this up. This shows what we call the electromagnetic spectrum. It encompasses everything from long-wave radiation down here, radio TVs, it's a little shorter wavelength. Shorter wavelengths is microwaves, so that's a wavelength here. And then even shorter is thermal, thermal IR, then you get an infrared, you get an visible. The red of the visible portion of the spectrum is longer wavelength than the blue, which is higher energy, shorter wavelength up here. Then all the way to ultraviolet, where we can't see, X-rays and gamma rays being some of the highest energy. It's really all the same thing. Only the real difference is the wavelength, peak to peak distance, and what we call the wavelength. We'll talk a little bit about that in just a second, but what I wanted to focus on, when we're talking about sunlight, this is really where we're at, the visible part of the spectrum as far as what we can see. And that's what we're interested in right now. This chart here on the same Wikipedia page does a little better job of showing the effect of the wavelength at these different energy levels. Let's blow this up. Okay. Shorter the wavelength being peak to peak length, say from here to here. You can see that distance between peaks gets shorter and shorter as you go this way. Radio waves down here, very low energy, they don't harm you. Gamma rays, very high energy, they harm you. The visible portion of the spectrum is in the middle here, a certain bandwidth that we just talked about just a minute ago. So this shows how the wavelengths changes depending on the kind of energy you're looking at, but it's all electromagnetic energy. This is another Wikipedia page on sunlight. This is going to show us the energy distribution in the solar spectrum. Let's blow this chart up here. Okay, this is the spectrum of solar radiation. This is radiance, energy level basically coming to the Earth. And this is wavelength. Now wavelength is increasing this way, which means your energy level is high here because it's shorter wavelengths, lower over here because it's longer wavelengths. So you can see here, this is the UV part of it. You don't really see this. This just burns your skin. And obviously does other damage to various things. It does some good things too. Let's focus on the visible. That's in this portion of the spectrum here, but then you've got this long tail out here in the infrared region. But basically here we are, this portion of the solar spectrum is what we're talking about today. This is a wireframe model I made to represent how the electric and magnetic vectors are oriented relative to each other. And as a photon of light progresses through space, we're just arbitrarily letting this red wave here represent the electric field and the green the magnetic. As you can see, they're 90 degrees to each other. Okay, now when light comes off most sources, there's no particular orientation this way or that. And you don't see that. And in fact, normally light's not going in one direction, scattering and what have you, unless you've got laser light involved. But for this case, And now, when a photon of light's going through space, it's not going up and down. What's happening is the electric field, let's just look at the electric field. Forget the magnetic field for a second. The electric field is maximized here. As it progresses, it minimizes, then maximizes, minimizes, maximizes, minimizes, maximizes. Now the wavelength is basically the speed of light divided by the frequency. Most scientists use wavelength rather than frequency to talk about electromagnetic waves. Peak to peak is the wavelength. And so that's important to know, because for longer wavelengths like infrared or radio waves, these things stretch way out. For real high energy radiation like X-rays, they're going to get really close together. So that's, again, this is just to represent how that might happen. So you don't have this going through space. You have a photon of light with the field oscillating as it progresses through space. Okay, next reasonable question would be, well, okay, what is polarized light, and how do I make it, or how do I look at it? This is a piece of polarizing film that I purchased off Amazon. I'll put a link in the description. This happens to be polyethylene terephthalate, going through a special treatment process, mostly oriented in one direction, and possibly coated, or possibly have special things in the polymer mix. But if you actually just Google or use Bing ChatGPT to look up polarizing film, it'll quite often just tell you they use polyvinyl alcohol, uniaxially oriented, or oriented in one direction, not two directions. Then maybe treated with iodine or something. But anyway, this is a piece of film. Now let's kind of show you what's going on here molecularly with this. It kind of helps this polarization process. In other words, why would light only go through oriented in a particular orientation? We're going to kind of make a simple experiment to show you how that might happen. Okay, imagine that this is a chunk of plastic polymer that you're going to turn into a polarizing lens. And you got long molecules of the polymer just oriented randomly. Now, if you stretch these in one direction, this is just obviously a crude demonstration, but watch what happens. See how the molecules line up in that direction of stretch? That's your polarizing material, as exemplified by this. That would be the direction of polarization. As far as light interacting with a polarizing film, we're only going to worry about the electric field side of this. So imagine that this is one direction oriented plastic film with coatings on it to make it react with light. Now, as you can see, if this was polarized light, the electric field it can go through it that way, but it can't go that way. So what happens if you have ordinary light back here, it goes through this, it gets lined up, say vertically in this case. You have another one of these and you orient it horizontal so that the field or the light's now oriented this way, it can't get through. That's how polarizing film can block the light. Just in a very simple way to look at it. Okay, this is a piece of the polarizing film. That light coming out through the blinds there, sunlight, it's relatively diffuse, no particular polarization. We'll see, let's rotate this different directions. Maybe a slight difference, but really not noticeable. Now I'm going to tape a piece of this on there. Okay, now we're going to hold this other piece in the same orientation. It doesn't block much. Now watch. Significantly blocks it when I rotate it 90 degrees. This really demonstrates it. Let's take a look at the polarized sunglasses. That's horizontal. It's vertical. Almost a total block that way. So definitely polarized sunglasses. Now let's look at my non-polarized sunglasses. See? Minimal difference. That's the difference polarization makes. All depends on the angle, relative angles. And this is my Minolta polarizing lens. I don't really know which way is what on this as far as orientation, but it is a pretty effective polarizer. See that? I can rotate it around, get a total block and a total pass. Basically a total block of that polarized light coming off the film I have taped on there. I've got both sheets of my polarizing film laid on top of each other to kind of magnify the effect. See the sky, how blue it is? Now watch what happens with this polarizing film when I rotate the direction of it. See how it darkens? You can tell then that that light coming in that direction is polarized. Let's do it over that way. Really, sun's so bright out here, it's hard to see. Let's look over this way. Now, the sun's almost, it's roughly 45-degree angle on the sky. It's about 1:28 in the afternoon, but you really do get a dramatic effect over this way when you rotate the polarizing film. This is a cloudy day. Let's see if there's any noticeable polarization with this. Not really. I don't think so. Let's look over here. Don't think so. I can't see any indication of polarization on this cloudy day like we could on a clear blue sky day. This is an AI overview I got off of Google about why the sky is polarized. And they're saying here it's due to this so-called Rayleigh scattering, a process in which sunlight is scattered by particles and gas molecules in the Earth's atmosphere. How it works. The electric field of light waves causes charges within particles to move at the same frequency, turning the particle into a radiating dipole. This radiation is what we see as scattered light. Light's blue. Scattering of light depends on the wavelength. With shorter wavelengths, blue light, scatter more stronger than longer wavelengths like red light. This is why the sky appears blue. Now, why it's polarized? The scattering process partially polarizes the light. The polarization pattern of the sky is determined by position of the sun, with the maximum polarization occurring in a circular band 90 degrees from the sun. How to see it? You can use a polarizer on your camera to enhance the blue colors in the sky, as we did with that film. Okay, we've got a nice clear blue sky here. This is my Minolta camera lens, it's a polarizing lens. I'll watch it if I rotate it. See how dark, how kind of light blue there? See how it darkens? Just by rotating that. That's because that light up there is polarized in a particular direction. We can block it when we're at right angles to it. This shows it really well. Now there's not as much effect. See, the sun's to the upper right. It's right in my eyes. Look in this direction. There's a little bit of effect. You can barely see it like you could over here in this other direction. See the glare on the windshield? Now I'm going to put this camera polarizing lens right over the iPhone's camera and rotate it around. You can see that glare will change as I rotate into different positions. You can really block some of that glare with a good polarizing lens. It's hard to see with this, but I just putting on these glasses, the surface glare that keeps you from seeing through the windshield is greatly reduced with these polarizing glasses on. When I turn them like that, I get maximum glare on the surface. So the orientation of the polarization in these glasses is the right way for reducing that type of glare. See all that reflected glare on the pond? Let's put this lens over the camera, iPhone lens. I'm going to rotate it around. You should be able to see a difference in the amount of reflected glare as I rotate it in different directions. I'm going to take a quick look around the house to see if I can see some light sources that are polarized and which ones are and which ones are not. This is my iPad. It looks like a slight polarization. You can see it darken a little bit as I turn it. Got Alexa over there. Let's see.
I'm not quite sure how to help you with that.
Well, Alexa thinks I'm asking. There is a slight polarization there. Now let's look at this lamp, just an ordinary LED bulb in there. Nothing. Same thing here with these light sources. This is my iPhone 12 Pro Max, with the sheet oriented along the same direction as the landscape orientation. Not much, but you do see a darkening when it's diagonal. That's the maximum darkening, is when it's diagonal. Either directly oriented with it or perpendicular is not as much, but diagonal there is. Interesting. This is the display in our 2018 Model 3. Now I do have a anti-glare protector on that display. So let's look at it. This is the film. Let's turn it. I don't believe doesn't appear, if there is an effect, it probably is a little bit, it's a little darker that way when it's vertical than it is that way. Slight amount of polarization, not a huge amount though. I'm going to look at the TV and see if it's a Samsung 65-inch sheet-oriented landscape just like the TV, but now watch what happens if I rotate it vertical. Almost totally blocks it out. No question that light coming off the TV is polarized. Hopefully this video has given you a good idea of what polarizing sunglasses are and how they can benefit you in eliminating certain types of reflections or make the sky look bluer at certain angles. And these are the non-polarized, these are the polarized, your choice. And also, if you have a camera that can accept a polarizing lens, like this Minolta polarizing lens I have, it can really give you some interesting effects. So, hope you enjoyed this and got some better insight into what polarized sunglasses are all about and what polarized light is. And if you did, please like the video and subscribe. I'd really appreciate it. Thank you.